Okay, Bismillahirrahmanirrahim. Welcome to the Structural Engineering Software Application, lecture number 9. In today's lecture, we will discuss how to perform earthquake analysis of structure in SAP2000. Okay, the lecture's outlines are objective of today's lecture, introduction to earthquake, UBC 97 seismic parameters, seismic loading criteria and methods, uh, example on earthquake analysis of structure, and at the end class task for the student practice. Okay, lecture objective. By the end of this lecture, the student will be able to analyze different structures subjected to seismic loading in SAP2000. Introduction to earthquake. Earthquake result from the sudden movement of the tectonic plates in the earth crust. Okay, the movement taking place usually at the fault lines causes energy release which is transmitted through the earth in the form of waves. These waves reach the structure causing shaking or earthquake. In the figure, occurrence of earthquake is shown due to fault rupture at this location. Okay, when the fault is ruptured, so the sudden energy will released in the form of body waves and surface wave. Right, when these waves hit the foundation of the building, it transferred all the waves energy to the building, and the building start to and fro motion, and ultimately the structure will failed. Okay, and the other picture, some terminology related to earthquake occurrence is given. Okay, fault rupture point is called focus, right, and the point above focus on the ground surface is actually called the epicenter, and the distance between epicenter and focus is called focal length or focal depth, and the distance between the epicenter and the place of interest is called epicentral distance. Okay, earthquake magnitude is actually in the form of acceleration, or it is also in the form of velocity and displacement. Okay, the figure shows the effect of earthquake on the building. Okay, when earthquake hit the building at foundation level, it displaced the building in that direction. Okay, but due to the inertial forces or the mass of the building will remain at a location where it is placed, or it is moved in the opposite direction to the earthquake. Now, because of the inertial forces and earthquake forces, this lead to the displacement of your structure, right, and ultimately it lead to the failure, and it depend on the design of structure. This slide I will discuss how the gravity load effect is different than earthquake load effect. Okay, in case of gravity load, the direction of that gravity load will be same, and also the magnitude, and similarly the responses against gravity load will be also remain the same, like the shear force and the bending diagram will be remain same. But in case of earthquake load, what happened to the responses of structure? Actually, in the earthquake load case, the reversal of stresses take place during the tension become compression, right? So in case of earthquake, the tension is converted to the compression, and compression is converted into the tension in the different phases and different modes of earthquake shaking. Okay, that's why the earthquake response is compared to a gravity load is very uncertain. We cannot determine either there will be tension or compression. And similarly, the design of gravity load is definitely will be different than design of earthquake load, right? So in the earthquake load, the reinforcement will be provided in the both phases, right? Similarly, the splicing, location, hooks, angle, steel requirement, and the grade of steel, and the different dimensions of the member is also very important. Similarly, the joint reinforcement is also will be considered while designing for earthquake load, and there is no special provision required for gravity load, is just like required for earthquake load. Okay, I will use UBC 97 code for analysis of structure against earthquake in SAP2000. So that's why the seismic parameter is very important, that is given in UBC 97. The specific site detail. Okay, so there is some specific site detail which is required to model seismic load. Seismic zone. Pakistan is divided into 4 different seismic zones. Okay, in zone 1, the peak horizontal ground acceleration is very small, that is 0.05 to 0.08 g, while the seismic zone 4 is a very critical zone where the peak horizontal ground acceleration is more than 0.32 g, where G is acceleration due to gravity. Okay, from seismic zone, the seismic zone factor is determined, and the seismic zone factor values is given in table 16.1, right? For zone 1, the Z value is 0.075, and for zone 4, its value is 0.4. Okay, the second parameter in this specific site detail is soil type. Okay, soil type is usually divided into different types represented by SA to SF, right? SA is represented hard rock, while SE represented soft soil profile, right? If the soil is not included in the above types, so there is another type that is represented by SF, and it required certain site specific evaluation. Now past earthquake magnitude, and it is very important seismic parameter, and it depends on the seismic source type, right? And actually it depends on the fault that is capable to produce different magnitude events, right? In the UBC 97, seismic source type is divided into three different types, A, B, and C. So seismic source type A means that faults that are capable of producing large magnitude events and that have a large rate of seismic activity, and the maximum moment magnitude is more than 7, and slip rate is more than 5. Similarly, in source type 2B, all fault other than type A and C, right? Similarly, in seismic source type C, fault that are capable of producing large magnitude earthquake and that have relatively low rate of seismic activity, right? In this type, the magnitude of earthquake is less than 6.5, and the slip rate is also less than 2. Okay, now determination of seismic coefficient. There is mainly two seismic coefficient, CV and CA. Okay, keep in mind this thing, these both seismic coefficient depends on the site specific detail that I have discussed in the previous slides. Okay, for seismic coefficient CV, so you required seismic zone factor and soil profile. If you want to determine seismic coefficient CV value for soil type SC and seismic zone factor, for example for zone 3, so the value of CV will be 0.45. Similarly for CA, again if you want to determine for the soil type SC and seismic zone 3, so the value for that will be 0.33. Now determination of importance factor, and it is an additional factor and it is a kind of factor of safety, and it depends on importance of structure and facility. Okay, in the table the I values are given for different facilities. For essential and hazardous facilities, the I value is taken 1.5, and the essential facility include hospital, fire and police stations. In the hazardous facility include the different explosive or chemical industries and nuclear power plant. Similarly, for special occupancy, standard occupancy and miscellaneous structures, the I value is taken 1. Facilities are include the different residential buildings and schools and colleges. Okay, now determination of R factor. R factor depends on the overall structure for response under seismic and lateral loading. Okay, for structure that shows good performance, it means that R factor for that structure will be high. Okay, actually the R factor mainly depends on the different factors like the structure design and its configuration and arrangement of different members, the joint connectivity and the joint design. Okay, ACI divide the seismic design into three different categories of frame having special design provision, and it is called movement resistant frame system. And the three category of movement resistant frame system are special movement resistant frame, and that is represented by SMRF, then intermediate movement resistant frame and ordinary movement resistant frame. Okay, for special movement resistant frame, the R factor value for both steel and concrete is 8.5, and this value is much higher than IMRF and is compared to OMRF, because in SMRF there is a lot of additional requirement for designing against earthquake, so this give you good performance as compared to the other system. And that Okay, similarly, if you are considering the ordinary moment resistant frame for both steel and concrete, the value will be 4.5 for R, right? And for intermediate moment resistant frame, and the R value will be 5.5. Okay, now determination of structure time period. Okay, structure time period is actually the time required for one complete cycle. The structure time period can be approximated by using the following formula, right? Where Hn is equal to actual height, that is in feet or meter, of the building above the base to the nth level, and Ct is a constant, and 0.035 value when you are using the height in feet unit, and when you are using height in meters, so the value is 0.0853, right? And this first value is for steel moment resistant frame, and Ct is equal to 0.030 for reinforced concrete moment resistant frame and eccentrically braced frame, right? And Ct is equal to 0.020 for all other buildings. Okay, now seismic loading criteria and methods. According to UBC 97, there is two methods to apply a seismic load on structure. One is the static force procedure, and the second is the dynamic lateral force procedure. And dynamic lateral force procedure is further divided into two methods: time history analysis and response spectrum analysis. First of all, I will discuss static force procedure. In this method, the equivalent static force is determined, and this force is determined by using this formula, and we also call this static force a base shear, and where Cv is seismic coefficient, I is the important factor, then R factor, then time period, and W is the total seismic dead load of the building, right? And I have discussed all these different factors in the previous slides. Okay, the figure shows the equivalency between earthquake load and static force, right? Okay, when the building hit your building at base level, so the behavior or the response of structure will be just like this. Similarly, if we can determine the base shear and apply that at the top of the building, right? So in both cases, the response will be same. So that's why we can replace the earthquake response with the static force, right? That is base shear. Okay, the formula give you the total base shear. So for single story, so the total base shear will be applied over here. If the building is multi-story building, so for that you will divide the base shear, total base shear at different level of story. Okay, for that the formula is also available. Okay, in the one procedure in the dynamic lateral load is time history analysis. Okay, in this analysis, the time history of any earthquake previously occurred will apply to a building. For example, if this is the time history of any previously occurred earthquake, when this kind of time history is applied to a certain building, to obtain this response, lateral displacement and time, right? So, okay, the structure response will be either in the form of displacement, acceleration, right, at any instant of time. And usually design is performed for a maximum response of the structure. Okay, now response spectrum analysis. In the response spectrum analysis, a peak responses is obtained of structure having various time period under specific earthquake. How? Okay, for example, a specific earthquake is applied to a building having different time period, right? For example, this building is time period is 0.3 second, and for that is 1 second, and the other building having 2 second time period. When the same time history is applied to this different structure, so the response of each structure will be different, right? In the first response, the maximum response is D1. For the second building, the maximum response is D2, and for the third building, the maximum response is D3. Okay, then all maximum responses is obtained and plot it along Y and along the structure time period, right? So this graph actually obtained is the response spectrum, right? And this response spectrum is applied to a structure for analysis and ultimately designed against this response. Okay, now I will discuss an example on earthquake analysis of structure in SAP 2000. So I will discuss different methods one by one. First of all, static force procedure. Okay, this is an example. I will take any 3D frame and the rest of parameter required for earthquake analysis for static load is given in this slide. Okay, again the methods include three phases: phase 1, phase 2 and phase 3. Okay, now I will discuss phase 1. Okay, in phase 1 different steps involved. First of all, I will create a new model, then I will define and edit grids, right? Then I will define materials, define sections and define load pattern, right? For the static force procedure, I will define a load pattern for earthquake, right? And then I will define the load cases, load combination, then I will draw area element if any, then I will mesh area element, right? Then I will assign joint and loads, right? In this lecture I will discuss only the defined load pattern for earthquake, and for rest of the steps kindly refer to lecture number 3, 4, 5, 6 and 7. Okay, now how I can define load pattern. So for that go to define, then click on the load pattern. Okay, in the load pattern type I will select the quick, okay, from type, and I will define a load pattern for earthquake in long x and y direction. Okay, keep in mind this thing for both earthquake direction. So I will use UBC 97 code, right? Okay, once both load pattern are added, I will go to modify lateral load pattern. Okay, when I click on the modify lateral load pattern, so this window will open. So first of all I will choose global x direction, right? For the global x direction, so the soil profile type is SC in the example, then seismic zone factor is given, so I will enter the seismic zone factor. Then I will enter CT coefficient, right, for the time period. Then similarly I will enter the seismic source type, then the distance to the source, and then I will enter the important factor and R factor, right? And similarly I will repeat the same inputs for global y direction, right? Okay, once the load pattern for earthquake is completed, next step is to define load cases, right? For that go to the define, then click on the load cases, and in this step I will just change the scale factor, that is 32.2, and this scale factor is the value of gravity g value, okay, gravitational acceleration. And similarly load cases will be modified for earthquake along y direction. Okay, along with separate load cases I can also add a combination. Okay, once all the step in phase 1 is completed, then the model is ready for analysis, right? Once analysis is completed, then you can display different results, right? I will solve any 3D frame structure for analysis against earthquake under static force procedure in SAP2000. Okay, first of all I will create a new model, go to file and new model, and then I will choose a 3D frame template, and I will keep all the inputs by default and click on OK. Okay, once the 3D structure is completed, okay, in order to model a 3D structure kindly refer to the previous lectures. So I will just discuss here how to define a load pattern for earthquake. Then I will go to define a load pattern for earthquake. So go to define, then load pattern. Okay, so I will add a quick load pattern, that is earthquake, and first of all I will enter along x direction, and I will choose the UBC 97 code for this earthquake analysis, and then I will add this load pattern. Similarly I will add another load pattern along y direction, so I will add another one. Okay, once both earthquake along x and y direction are developed or created, then I will go to modify both load patterns. Okay, first of all I will modify earthquake along x direction, so select this load pattern and then go to modify load pattern. Okay, from here I will change the different inputs value including the seismic coefficient, near source factor and other factor that is required. Okay, in example I will check. Okay, the soil type is SD, right? So I will choose SD. right? And seismic zone factor is actually 0.02, so I will choose this, right? And important factor is 1, R factor is 5.5, and CT value is 0.03, right? CT value is 0.03, okay, and R factor is 5.5, and important factor is 1, okay. So all the entries are completed. Now press on OK. Similarly, I will again modify load pattern for earthquake along Y direction. First of all, I will change the global X direction to global Y. Okay, then I will change the soil type, that is SD, right? Then seismic zone factor, right? And then this value, that is 0.03, and R factor is 5.5, and important factor is 1. Okay, with this step the earthquake load pattern is defined. Then click on OK. Next step is to define load cases for the particular earthquake that is defined in the load pattern. So modify load cases, and then from here, the units are in inches. So here the value of G value in inches is 386.1. I will modify it, click on OK. And similarly for earthquake along Y, I will modify the scale factor 386.1 and modify the value. Click on OK. With this step the modeling is completed. Now we can perform analysis. So click on run analysis, run now. Once the analysis is completed, then we can display different results. First of all, I will check the deform shape. So go to display, then show deform shape. So I want to check the deform shape against along earthquake X direction. So click on OK and start animation, right? So this will give you the static response of structure. Display the deform shape along Y direction. So change the case to Y, right? So it will start to and fro motion along Y direction, right? So this is the static force procedure. Similarly, I can display the other results like shear force, bending moment. So for example, if I want to display the bending moment diagram, go to display and then show forces and stresses. So from here I will value for earthquake X. So click on OK. Similarly, if you want to see along with the values, and you can also display the shear force diagram, right? And we can also display the joint reaction, right? So this is all about the static force procedure. Now I will discuss example on earthquake analysis of structure by using the dynamic procedure. First of all, I will discuss time history analysis. In phase 1, again the following steps are involved. All the other steps are same, just like I have discussed many times in the previous lectures. So in today's class I will discuss additional steps that involve to define the function for the time history, right? And I have to define the load cases for the given time history along X and Y direction. For rest of the steps, kindly refer to lecture number 3, 4, 5, 6 and 7. Now how to define function for time history. So for that, go to define, then click on function, then select time history, right? So this window will open. In this window there is a variety of different functions type are available, but we will choose from file. So we want to import time history for a particular earthquake, so I will choose from file, right? When from file will click, so this window will open. So you can browse the time history at this location, right? Okay, once actually the time history is available in the SAP directory. So for that you will browse the program file, computer and structure, then SAP 2014, and from there you will click on the time histories, right? So the different time histories file will be open. From here you will click on any time history. For example, I want to import the El Centro time history, so I will choose the El Centro and click on OK. So the El Centro time history define the name for this time history. Then we can display the time history the graph in two ways. One is the time and function values that is currently displayed, and the other is the value at equal intervals where the responses are displayed in equal interval of time. Okay, you can also view that file which contain different data of time history. So if you click on the view file, so that file will be displayed. Okay, above there is three different entries. One is the header lines to skip. Okay, when you open your files, so if there is some heading involved in the text involved in the top rows, so kindly you can skip that particular lines, because otherwise it will consider that responses from the file as well. If there is no header line, so keep it to 0. If there is one header line, so skip one header line, and similarly if there is 2 and 3, so you can skip the line accordingly. Okay, similarly if there is some prefix are available, so you can also skip that lines as well. Okay, and there is another entry, it is called the number of point per line. Okay, when you click on the view file, so there is different points are given in one row, right? If only one point is given, it means that there will be two values, one for x and one for y, means one for the time and other for the response, and the response will be in the form of acceleration, displacement and velocity, right? So this will be considered a 1 point. If there is total 4 entries, so it means that 2 points are there, so you will enter 2 points. If there is 6 entries are there, so it means that the total points per lane is 3, so you will enter 3, 2, 4, or it depends necessarily that you will import your file, so you can also create your own file. Okay, for user define, you just click on the user define. So this window will appear. In this window you can enter your time and values, right? In this when you enter your time and value, so click on add. Similarly you can add multiple values in this window. Okay, once the time history function is defined, next step is to define load cases for time history along x and y direction. So go to define, then load cases, and add new load case, and where I will enter I will define load case for time history along x and y direction. So when this window will open, so first of all I will change the load case name time history x, right? Okay, from load case type I will change static to time history, right? And then I will enter load values in the load applied. First of all I will change the load type to the acceleration, then I will enter load name u1, u2 and u3. Okay, u1 actually give you the displacement in the x direction, and u2 means the displacement in the y direction. So I want to define the load case along x direction, right? So I will choose the function that I have defined in the previous step, and I will then enter the scale factor. Okay, for feet per second square, so the g value is 32.2. Okay, similarly I will enter the time history load case for thy, and the rest of it will be same except u1 I will just change u1 to u2. Okay, with this step and all other step included in phase 1, so then the model will be ready for the analysis. So then I will click on the run analysis, then when run analysis is completed, then I can display different results. Okay, now I will solve any 3D frame example in SAP2000 for time history analysis. Okay, first of all I will create a model, right? I will I'm taking 3D frame and keeping all the values by default. Okay, once the model is complete, then I will define function for time history, then go to define function and time history, right? Okay, from here I will just select from file and then I will add new function, right? I will change the function name to th and then I will browse the time history. Okay, so it is already I am here, so you will just go to C, local C, then program files, computer instructions, SAP2014, then click on time history function. Okay, okay, from here show all files. So from the show all files to all different time history will be opened. So I want to import the El Centro time history, so select this one and click on open, right? So the El Centro time history is imported. Okay, we can display the values in the form of time and function if you want. So display, so it will be displayed in this way. Similarly, if you want to display in the other way, so this value will be in this format, right? Okay, in order to view the file, you can just click on the file, check how many values are there in one row. So actually there is 6 entries, so it means there are 3 points per header, right? And there is no line to skip because keep the header values 0 0, but the number of point per line are actually 3, so I will keep it 3, and again I will go to time and function and display result. So now the complete data is displayed over here, right? Similarly, you want to check the value at equal interval, so the value at equal interval will be shown. Okay, but we are interested in this format. So similarly, if you want to switch to the user define, so from here you can also enter your own values and by adding it, right? So click on OK, right? So this time history is defined. Okay, next step is to define load case. So first I will add a new load case, right? And that load case will be for THX, and I will change static to time history, right? And from here load type to acceleration, defining for THX, so I will keep U1, then the function is TH, and the value of G is in inches per second square, so it will be 386.1. add this one. Okay, the rest of value will be same, click on OK. Then again I can add copy of this time history. I will just add copy of this load case, and I will just change the name of cases, and then I will change U1 to U2, right, and modify it. Click on OK. So the time history along X and Y direction are defined. Okay, now the model is ready for the analysis. Then click on the analysis. Okay, once the analysis is completed, now we can display different results. So for example, if I want to check the deform shape, then change the load case to TX, for example, click on OK. You can see, so this is the time history function is applied in X direction. Similarly, you can check the deform shape along time history Y. Okay, and start animation. Okay, keep in mind you can slow down your animation by this tab. Okay. If you want to slow down your animation, so you can bring this portion to the left side. Similarly, you want to increase the animation speed, so you will increase the other side. Okay. Similarly, we can display shear force and bending moment diagram. So for that you go to display, then show forces and stresses for frame, so for THX. So similarly, I can also check the shear force and the bending moment for THY, right? And you can also display the joints reaction. For case THY, So this will be the joint reaction. Okay, this is all about the time history analysis in SAP2000. Okay, now I will discuss with the help of example how to analyze structure against earthquake by using the dynamic procedure and by using the response spectrum analysis. Well, again, I will go through phase 1, and in phase 1 contains the following different steps, and I have discussed all the steps in lecture number 3, 4, 5, 6, 7, except the define function for the response spectrum and define load cases for that particular response spectrum function. Okay, so I will just discuss step number 6 and 7. So for the rest of steps you can refer to the lectures given in this slide. Okay, now how to define a function for the response spectrum. So again I will go to define, then function. So from function I will just choose the response spectrum. Okay, right, so I will choose the UBC 97, click on OK, right. So this window will open. Okay, in this window you can define the name of this function, right. Then define the function damping ratio. Okay, what is the function damping ratio? It is actually the dimensionless measure describing how oscillation in a system decay after disturbance, right. And in this response spectrum analysis I will define a response spectrum for a particular earthquake. So what I will do, so I will just define the seismic coefficient Ca and seismic coefficient Cv. So these both factor depends on the multiple parameters, so that I have discussed in this lecture in previous slides. Obtained Ca and Cv value is 0.4, 0.4. So this will develop a response spectrum. So here is the response spectrum entries, responses, values. This is in the form of period and acceleration. Similarly, if you will change Ca and Cv value, so the function graph will be changed accordingly, right. You can also convert it to the user defined. The function is defined. Next step is to define load cases for response spectrum function along x and y direction. So okay, again I will go to define the load cases, then I will add new load case along x and y direction. I will add along x direction. So I will change the load case name for is response spectrum x, right. Then I will change load case type to response spectrum, right. Then I will enter the loads applied. I will change the load type to acceleration. Then I will enter the along u1 u3. Okay, we can also define a load case where the earthquake response is in either in the x direction, also in the y or z direction, right. When the response spectrum for both along x and y direction are defined, so then we can go to the other step, that is analysis step. Once analysis is completed, then I will go for post processing, where I will display different results. Now I will solve any 3D frame structure in SAP2000 for response spectrum analysis. I will create a new model of any 3D frame, right. Okay, then I will define a function for response spectrum. Go to define, then function, then response spectrum. So I will choose UBC 97, right. Then add new function. Okay, and I will change the name to the response spectrum. For example, the Ca value, if I change the Ca value, for example, it is 0.2 and it is 0.1. So you can see the graph value, the graph function will be varied accordingly, right. And I can also convert it to the user defined by click on the user defined. So it will be converted to a user defined. You can enter your periods and acceleration. Okay, once your response spectrum is defined, then click on OK. Now next step is to define the load cases for this response spectrum. Then click on load cases, then add new load case, right. I will change the response spectrum along x direction, the name of load case. Then I will change the static to the response spectrum, right. So I will define along u1, and the g value will be the scale factor 386.1. right? So the response spectrum along x direction load case is defined. Then I will add copy of this load case, and I will change the name to RY and change u1 direction to u2 and modify it. Then click on OK. Okay, once the load case is defined and all the rest of steps in phase 1 is completed, then the model is ready for the analysis. Then I will click on the run analysis. Then the analysis is completed. Now we can display different result. For example, if you the deform shape along x direction, so click on OK, then start. So this will give you the response against x direction. Similarly, we can check the response against y direction. Click on the deform shape RXY, click on OK. So this will give you the deform shape along y direction subjected to the particular response spectrum. And display the bending moment diagram and the shear force diagram, and also we can display the joint reaction. Okay, this is all about the response spectrum analysis in SAP2000. Okay, now class practice task for the student. Analyze the given structure that is given in next slide, this one. Okay, kindly analyze this structure for the following. For the earthquake analysis by using the time history method. So the time history values are given in this table, and then response spectrum criteria, then also perform static force procedure, right? Okay, consider seismic parameter given on slide number 18. Okay, thank you so much. This is all about lecture number 9.